Hey folks, let's sync this video and well, dive in. Because today we are talking about overfitting. I know I've alluded to this a bit and there are some lecture notes, but this topic is pretty important, so we're going to cover it. Let me just get everything. Want to zoom view? Yeah, okay. And hide toolbar. Okay. Cool. So prediction, overfitting. I already said that. Prediction. So we're going to start with a motivating example that I think all of us can relate to. Spam. Not the meat, the email. So here's our data set. It's from the open intro package, and so you should have access to it. But anyway, it's a set of emails, and we know whether each of those emails is spam or not, as spam or is not spam, as well as some other features that we'll crawl into. And what we're going to do is use logistic regression to predict the probability that an incoming email is spam. And we'll use model selection to pick the best model in terms of predictive performance. Now, building a model to predict our spam is only half the battle. We are going to need some kind of decision rule to decide whether an email gets flagged as spam or not. Effectively, what probability we should use as our cutoff. So this most simplistic and straightforward approach is choose a single threshold, and any email that exceeds whatever our threshold probability is gets flagged as spam. Yeah, so to illustrate, here we've got a big regression model with pretty much everything in the kitchen sink, predicting the relationship between spam and everything else. And now that I'm staring at it, I'm realizing why it keeps spitting out the GLM algorithm error that you can see on the slides. And it's because we have overfit our model, which technically I knew was kind of going to happen because in our model we're effectively fitting everything. But as you can see here, we have terrible standard errors that are just huge. So what I'm going to do while we are all here together is fix it with you. And this will serve two purposes. One, it will refresh my soul, so to speak. And it will what else will it do? It'll hopefully solve some of these problems. So what I'm going to try, as we can see here, this model has everything in the kitchen sink in it, literally by the dot. So let's see if we can fix this. So part of this is the problem is tidy models, because tidy models are a pain in the ass. to be frank. And I don't find them intuitive at all. So, okay, let's GLM. Okay, plug in our. So what I'm doing here is just converting our tidy model into our a regular human readable model that doesn't give us standard errors the size of houses. Okay, so we got formula. We want spam as a function of, let's just start with from. Just pick one and from plus sent email. Metadata equals email, comma, family equals. We want a binomial function to start. And then data. Oh, we already did data. All right, let's see if this works. Okay. Well, this one may be converged. What I'm doing here is adding the summary function so I can actually see if it's meaningful. There we go. Okay, summary didn't really give me. Okay. Okay, well let's pick something else that, yep. Let's see if that helps. Because there is an association between these two. Well, there should be. Okay. Huh. This is bizarre. Ah. Okay, let's try. What I'm doing is seeing what the actual names are. Okay. How about this? Oh wait. Wait. Okay, so okay. Wait a minute. Okay. So I have just come to a realization that I've made so much more work for myself because when I cleaned up this data, and you don't actually see the data cleaning process, I added an extra variable for my own bookkeeping, having a numeric version of the spam variable, which then I'm using to predict a function of the spam variable. And they're perfectly predictive because they're the same variable. What does this all mean? Well, not much now that I've figured out what has happened. Fun facts. Okay, so let's go and fix some code together. Okay, cool. We're gonna open up, because if I don't do it now, I will forget. Yeah, so in addition to what I'm doing now is just making sure that the lecture notes that accompany these slides, okay, the logistic, open, cool. Yeah, okay, fixing that. Okay. So in my attempt to kind of streamline footage, I've put most of the technical notes related to this module, like the logistic regression as a logit function and all the details about interpreting and estimating and making sure that all the criteria are met. Those are here. And everything should work now. Okay. So let's go back. Well, I'm still here, so we'll actually move ahead. We're going to recompile. I'm going to first tidy this up, the environment, because I broke my overfitting, and I'm going to rerun it with you here. Cool. Cool. Warning messages fitted probabilities numerically 0 or 1 occurred. Cool. That's fine. This is a different warning that I'd been grappling with all freaking day. Cool. Anyway, let's actually dive in to the lecture. View, we're going to hide our toolbar again and Zoom viewer. Cool. Prediction. Overfitting. Let's start with prediction. So, our goal today is to build a spam filter. And our data set, which you've just witnessed me grappling with to illustrate good troubleshooting, is a data set where we already have spam or email either classified as spam or not spam, as well as some other features of that data. Now we're going to use logistic regression to predict the probability that an incoming email is spam. And I have lecture notes that build us up to logistic regression, so please read those before you watch any more of these slides. In theory, the video with the slides, because I know a lot of the regression is either like review or something totally brand new, so I figured I'd put it as lecture notes and just walk through like the application. But anyway, yeah, spam filters. We're modeling them, and we are going to pick the model that has the best predictive performance. What do I mean by that? Well, we are going to literally build a model that predicts the probability that an email is spam. Now, this is only half the battle because we also need decision rules on which emails get flagged as spam, because we have to use our model to make predictions and then make decisions on those predictions. Now, similar to a lot of work I do with model selection and model fit criteria, is we have to make decisions based on a rule. Now, the rule you're probably most familiar with is p-values, if something is significant or not. That is a decision, and the convention is 0.05. But so that if something is in the 5th or 90, well, the 2.5 or 97.5 percentile, we declare that unusual enough to reject that it comes from our null distribution. Similarly, we are going to have to pick a threshold to suggest that our spam classifier, that an email is unusual enough and different enough from spam, or different enough from what we would expect as regular email, to reject that it's a regular email and classify it as spam. Same idea. And so we have to pick the cutoff. Now, the most simple approach is to choose a single threshold for our probability. And then any email that exceeds that threshold is spam. Done. But, oh, this is so much better. But as we can see here, we have a lot of data in our model. And I am not going to tinker with the code because you saw me struggle with this. But anyway, we have a lot of things that change our prediction of the likelihood of something being spam or not. And we can see that there's a lot of stuff here that's definitely interesting. So, prediction. The mechanics of prediction, very straightforward. This is what we've been learning this entire time in your entire career at Wake Forest, and you'll be using those tools in the future wherever you go. And so what we do is we plug in values into the estimated model and give us a calculated response outcome, our y hat. Everything, all the modeling we do is to predict y hat. And ideally, a good model has got a really close relationship between what our actual outcome is and our predicted. But getting this right is hard. Really, really hard. And there is no guarantee that you have the correct model estimates for your prediction, or that your model is going to perform even remotely well on new data. Because your model and the predictions you make from that model are only as good as the data you give it. And they are very dependent on that data. To illustrate, here is a ton of lovely data in gray splotches, as well as 3 lines to make predictions from. The first line, the one I've labeled as underfitting, is in dark blue. And it is just a straight line. It's got a little bit of a horizontal tilt to it, so it has a slightly negative slope. But it really doesn't explain our data well. Technically, it minimizes the sum of squared errors, so it is the best fitting line for a linear approximation. But if we look at our damn data, we can see that that line is not useful. But if we go the opposite direction and really like trace along and really hit as much of our data using some kind of weird spline smoothing function, we get a really spiky mess that is clearly overfitting and like being pulled from the more general shape that is the purple line in the middle. It's a nice parabola. Okay, so there are several steps in order to make a useful model. And I know I've kind of hand waved my way through those steps here, kind of on what our values are, because I judged that, well, the underfitted line, not great. The overfitted line, also not great. And so we got a Goldilocks line in the middle. But that is a judgment. And in order to get to that point, to assess our performance, we first need to estimate our parameters, and then select our model, and then evaluate performance. So we can do this all with the data we have. But if we do that, if we use all of our data to make our model, sure, that's going to be awesome at explaining our data that we have. But that can lead to overfitting because we have to make a model that is useful beyond the scope of our data. So one trick to do this, and this is much more of a machine learning, data sciencey thing, is to allocate specific subsets of our data to do different tasks. So this is as opposed to allocating our entire model, all of our data, to estimating the model parameters, which is what we've done so far. But there are other ways that, frankly, are a little more replicable, in my opinion. However, I have the luxury of lots of data, while other folks may not. So it is a different choice. So let's talk about splitting our data. So in most kind of prediction frameworks in industry, at least from a machine learning and data science and just robust methods of estimation, we want to split our data at least in two pieces. One is our training set. This is our sandbox for model building. We are going to exploit the hell out of this data in our training set. It's where we spend most of our time, where we develop our models, and usually we eat up about 80% of our data because we do want a good model. We want to be able to make good predictions, and we don't want to waste all of our data or on just testing out our model. So we have to kind of find the balance. In the general sense in the field, and this differs obviously by area, is that you spend about 80% of your data, so the majority, in your training set to make a good, solid model. And then we use our reserve sample, our holdout piece, our testing set, to see if all that modeling that we did is actually useful. Do our models explain this holdout piece of our data? And this is really critical to look at once. Otherwise, it becomes part of the modeling process. So you can only use this once. So you better be happy with the data and the design choices you've made. Usually this is about 20%, but this really depends on your data sample size. And you may be familiar with this, the idea of kind of cross-validation. Effectively, that's what we're doing here. So here's some nice, lovely R code to split up our data. I've set a seed here for 1066 because I'm playing the Norman Conquest right now in another game. So that's why it's 1066. But yeah, so we're setting a seed to enable our analysis to be reproducible. And what I mean by reproducible is that if I run this again, if you run this again, you should get the exact same result as long as you set the same seed, because we're about to randomly split up our data. And so we're going to put 80% of our data into our training set and the remainder into our test set. And here we've effectively done that. by using the initial split function. Then we create two separate data frames so that they really are separate, and then we label these train and test. You have to be pretty careful about not mixing these up, because just like with any flavor of exploratory versus confirmatory analyses, you really need to keep them separate so that you can actually trust that your confirmatory findings are real and not just wishful thinking or subconscious bias or overfitting or p-hacking or data fraud. I mean, obviously these range in escalation, but we need to separate them out. Okay, so here I've shown us peaks of both. It's okay to look at them, just not model them until you're ready. Because the second that you fit your data to the test data, you've used it. And you now have knowledge about that split and that data, and so you can't keep reiterating and effectively then incorporate your test data into your training set. It's a very important distinction, and I'm very happy to talk more about it. But the point I'm trying to make here is that we have two separate data sets now. They're from the same source, but they're separate. And in our training data set, we have 3,100 spam and email, versus in our test data set, our holdout, we have almost 800. 80%, 20%.